it going? Got to give the people, get the people what they want. The people want to stop seeing me. They're tired of me. You know who they want to see? Boom, right there, Miss Reese in the house.
I'm back. It's been forever. Good to see you guys. Homework video. Super pumped. All right, today is going to be a really important lesson on simplifying radicals, like a major property of radicals, and how we prove a radical answer. You guys know that proving our answers is like our jam in Algebra 1 right now. Mr. Bass agrees.
I get juiced. Juiced about proving my answer.
How could you not prove your answer to see Mr. Bass like that? I mean, come on. All right, guys. So we're going to go ahead and start with this title called the product property of radicals. Product has to do with multiplication. That's going to be a big theme of today's homework video. So please go ahead and write this down. We're going to go ahead and state kind of two big definitions of this property to start, go through some examples, and then see why this property is important. So here we go. This property states that if you have a radical times another radical, you can actually smash these two radicals underneath one radical if you combine those two things with multiplication there. So what I'm saying is that the square root of a times the square root of b is equal to the square root of a times b. Now equality has two directions, that's what it states, so we could also reverse our property here and say, you guys have seen this before, that if we have something that we could pull apart or separate with multiplication, we can, like the square root of a times b, we can separate them into their own roots. Square root of a times the square root of b. This is some really big Algebra 2 stuff, and this property is really important, not just in Algebra 2, but in geometry, and of course right now in Algebra 1. So make sure you have this down. We're going to go ahead and look at some examples that have to do with this stuff right away. I'm going to leave the first line up because that's going to help us guide the next couple examples that we're going to see with numbers. So here's our first one. The square root of 2 times the square root of 5. Now what I'm seeing here, guys, is that we have two separate roots connected with multiplication. What we can do here is combine them underneath the same root. So I'm going to show a quick in-between step, 2 times 5, which creates the square root of 10. Now you may be thinking to yourself, like, why is this property useful? Like, why is it important for me to know that two separate radicals can be combined into one? Well, the answer is because sometimes this is not going to be staying as a root for long and maybe turning into a whole number, which you guys like so much. So let's take a look at a second example that's going to show that. Let's say that we have the square root of 6 times the square root of 6. Using our product property, we can go ahead and combine them underneath the same radical. Let's go ahead and do that and see what number it creates. Be consistent, show my in-between step. And that delivers the square root of 36. I know you guys have that big long list of radicals ready to go. This is a square rootable number. What is the square root of 36, guys? Question popped up right there. It's equal to 6. Now I hope you guys are noticing some patterns here, right? We're starting with two of the same type of radical, we're multiplying them together, and then we're kind of getting that number without the root covering it. An interesting idea. This isn't a coincidence. That's because square roots and squaring, another way of writing the square root of 6 times the square root of 6, are inverse operations. You guys know a bunch of inverse operations, and this is kind of a new pair of them. So inverse operations that we know are addition versus subtraction, multiplication versus division. And now we have a new set. Square roots and squares cancel each other out, leaving us with just 6. Now guys, this is kind of like the shortcut version of what we just showed up here, but there's value in the product property because we can start with two radicals and end up as a not radical. Interesting. So this is kind of our product property when we are split from 2 into 1. Let's see why our product property is important when it comes to solving and, Mr. Bass's favorite thing, proving that our solution is correct. It's nice to be on film again. All right. So we're going to go ahead and take a look at this situation. X squared minus 5 is equal to 40. Please write that down. You're going to sense that solving quadratic, something with a power of 2, starts off in the same way as any linear equation is being solved with our inverse operations. So we have this reverse order that we're going to follow. I did this imagining my PEMDAS, but in reverse. So I'm going to start by adding 5 both sides. Inverse operations all over the place in algebra, guys. So subtraction versus addition leaves us with x squared alone. Here's where we have our new set of inverse operations. I'm thinking about a number squared from our property that we just saw before. We know that we can cancel out that squared power with a square root. Always balance both sides, guys. So if we affect here, we're going to affect over here too.
This is the inverse operation. To get rid of something squared, square root. She said it. I'm just saying it again. To get rid of subtraction, addition. To get rid of multiplication would have been division. To get rid of x squared, take a square root.
Yep. So I'm glad Mr. Abbas kind of said that for himself because this is a new set of inverse operations, okay? But the idea of an inverse operation is still the same, guys. We use them to eliminate, right, and isolate variables, which helps us get closer to our answer. So, question popping up, what's the square root of x squared? It's x. The whole reason we included a square root because of our square power is to get a value for just x on its own. Now, here we have a number that you don't see on your square rootable numbers list, the square root of 45. But we've been practicing the skill of being able to kind of break apart the square rootable pieces, the square rootable factors that are inside 45. So we're going to go ahead and use kind of our product property in reverse, which means showing that we can split this square root into 2 separate square roots connected with multiplication. Guys, all square rootable numbers come from numbers squared, so like 3 squared is 9. And I know that 9 times 5 are factors of 45, so 45 is equal to 9 times 5. We're choosing these 2 in particular because the square root of 9 turns into 3, so our final answer here is 3 times the square root of 5 with x equals.
Point this out. Notice, 45. I could have broken it down to like 15 times 3. But why would I not do that? Question popped up. I wouldn't do that because it doesn't help me. Can I borrow this for a second?
Please.
Right? The square root of 15 times the square root of 3. I still can't take a square root of 15, so that doesn't help. I still don't know the square root of 3. That doesn't help. 9 and 5 work so much better because at least I can find the square root of 9. I can't find the square root of 5, but I can figure out the square root of 9. That's why this is an important term.
Yep.
I'm out.
Thanks, Mr. Bass. Some solid interruptions by Bass today. So yeah, guys, 9 and 5 were chosen with great purpose, as Mr. Bass showed us with our not great choices, 15 and 3, because neither of those are square rootable, okay? We have a lot of number fluency, which means thinking about the right numbers and the right use of them. So here's where Mr. Bass and Miss Reese just get so excited. We want you guys to prove to yourselves that you know an answer is right. Number 1, it's a good look, okay? It's a good look to know that you're right. I mean, take my word for it. Number 2, this gives us some certainty about what our answer is, okay? And also, we've been practicing this habit since we started solving equations. So we're going to carry it over to this one too. I'm going to go ahead and rewrite our answer up here and then show how we are going to substitute it. Now our habit here of plugging our answer back in doesn't change at all we're still going to substitute or replace x with this, but what we're doing when we replace it changes a little bit because we have new operations, right? Roots and square roots. So I'm going to go ahead and get that set up. Need some more space. Okay, so our original equation was x squared minus 5 equals 40. And our goal is to prove to ourselves, to the math gods, that this is the right answer. So any other substitution, guys, we just replace where we see this with the information there. Now notice that I'm not just replacing x. We have an operation that's attached to it, x squared. So you guys are going to notice that even before I write what x is equal to, I'm going to include parentheses and that power. Okay, because that isn't what we're substituting or changing. We're changing what the value of x is equal to. All right, so here we go. Minus 5 equals 40. This part's weird. It's okay. Now this is where we're getting to kind of juggling exponent properties and radical properties too. 3 squared, guys, is going to be equal to 9. I'm going to go ahead and write this in kind of an in-between step, which is going to be the square root of 5 squared. So actually, maybe even before I write 9, I'm going to write 3 squared. So you guys can see that I'm squaring all pieces of the group inside. So 3 squared, it's not a surprise, I just wrote it, is definitely a whole number, 9. Now, square root of 5 squared. Okay, and this is where our inverse operations show up again. Root 5 squared is just 5. Mr. Bass, is there room over here on the camera? Okay, so I'm going to show this really quickly because the square root of 5 times the square root of 5, which is root 5 squared, is equal to the square root of 25. And guys, what is the square root of 25? It's 5. Okay, so this inverse operation is showing up here. I want to be really consistent and rewrite the rest of my equation because that's our goal, right? We want to balance here. It's like math inception, math inside of math inside of math. We have order of operations here. We start with our multiplication, right? 9 times 5 is 45. And 45 minus 5 is 40. I'm going to put a check next to that because I know that that is a true statement. That's going to prove that our answer is correct. So, weird looking answer, still some really hard evidence about whether we're right or we're wrong. All right, guys. So, get ready to see many, many, many more radicals and get used to the idea of when we have a radical in our answer, we still can prove whether it's correct or not. Yeah. All right. That's it, guys. We'll see you in class next time. Adios.